With greedy, yeah.
Yeah. V1 gets the first slot and V2 gets the second one.
Yeah, okay.
So, for V1, the minimum value is 0.7 plus epsilon to get the first slot.
Okay.
And for
Okay, so suppose V1 reports 0.6 then.
0.6,
Yeah.
but V2 then can get the slot.
Yeah, but V1 gets the second slot and pays 0.5.
Oh.
You see, because he doesn't care which slots he gets.
Yeah, so it would be
0.5. They both pay 0.5.
They have to be 0.5 or 0.5 plus a bit more.
Could be with some constant or something, but not can't use the reports to determine their value.
But I didn't get how 0.5 works in this case. Why not 0 for all of them?
Okay, 0, fine. V3 would then report 1, and he gets it for free. Okay. A good question. I like this question because it is tricky, you know, so, yeah, good question. Right, so if you pay less than V3, then V3 has an incentive to win the auction. So this is actually, this is the same as normal BCG setting, where you have 2 items for sale, and you have to allocate an item, you know, those 2 items to the bidders, because there's no, you know, notice there's no new agent coming. So this is the actual traditional setting, BCG setting. If you calculate the BCG payments, you will find the same thing. The transfers will be that they both pay 0.5. Because this is not only not a BCG setting, this happens to be the optimal allocation as well. Right? Greedy is not always optimal. In this case it is. So the highest, the goods go to the highest, people with highest bidder. So it's maximized social welfare in this case. And therefore, the payments are the same as BCG transfers. But that's just a note to make those link with those 2 variables. So the critical value payments in this case are the same as BCG. In this case. Was that any questions about these examples? Because this is the basics of online mechanism design. And there's a few assumptions we can make and we can relax. So how much time do we have left?
25 minutes.
Okay. So I guess I'll just go through one briefly. The second one is a bit longer, so I don't think I have time for that. Then we can break a little bit earlier. Okay, so what assumptions did we make? Just to review both of them. So the mechanism knows the interesting set a priori. So far, you know, in all the examples I've said the agents only wanted 1 item. But there are more interesting settings where maybe the agent wants 5 items. Right? It's not satisfied with 1 item. So the question is, does the mechanism know that the agent wants 5 items or not? Okay, so that's the question. And we've so far assumed the mechanism knows that he wants, for example, 1 item. That's what we assume. But maybe he doesn't know that. And the other thing is that the agent value can be represented by 1 dimension. So that means that if you have your bundle, say your 5 items, you're happy, and you don't want any more. That's sad. If you want more, you get more, that's fine, but it doesn't give you additional value. In many cases, suppose you have a fridge already, you may want a second fridge, right? Because you can sell it. So it has some value to you. The second value has some value, but less than the first. Maybe. Okay, so there's this, maybe the single value is maybe not enough to represent true preferences. And this is actually quite an open area still. So some progress can be made, but not much. If you're looking for some research in this area, this could be potential. Okay. So let's look at this first assumption, the unknown interesting set. So what if we don't know the interesting set? Okay. Let's look at this setting here. So it's a perishable goods setting, for example, the electricity, with a single-minded agent. So that means that he wants 2 units, and he only gets value once he gets 2 units, and he doesn't get any value for only 1 unit. Okay? So he has value 0 if he gets 1 unit, because suppose he still doesn't have enough electricity to go to work, so he doesn't derive any value. As soon as he gets 2 units, then he's happy. He derives some sort of value. Now, why can't we design an incentive-compatible mechanism? Why is greedy not incentive-compatible in these kind of settings? That's the question. Okay? So, I guess I should have given an example here. So here is perhaps an example. So in this case, think of it as V2. He wants both units, and he's only happy when he gets both units, if he wins both options, right? Otherwise, his value is 0. Okay? But in this setting, greedy only allocates 1 unit. Suppose what does greedy mean in this setting? Okay? So this agent wants 2 units, and the other guys are happy with 1 unit. Okay? So you could, well, what could greedy allocate? So greedy knows that if he has both units, he gets 0.7. So we could say, okay, let's allocate 0.7. Let's allocate this first unit here, and we may not know what's happening here yet. Okay? So let's start by allocating this unit to B2, because his value eventually might be 0.7, but in this option is maybe 0. But we could have an allocation rule that looks at what's the maximum value that the agent has once its number here units are reached, and let's look at greedy, which looks at that particular value. So it allocates this item, then it comes to this option, and this new agent has entered in the option, and now it changes its mind, the strategy changes its mind, and instead of giving it to this guy, we give it to this guy, right? So we've got a greedy allocation. Okay. So what's the utility of this agent? Well, it's 0, right? And the utility of this agent is 0.9. Okay. Actually, what's the critical value in that case? For this agent. Okay, so anyway, so I'll tell you, so it's 0.7. Something, because before, this agent was out of the market at this point, because he already had a unit and he was no longer interested. Okay. Now, this agent is in the market still, and still interested, because he wants that second unit and is willing to pay 0.7 for that second unit. So the lowest, so the critical value of this guy is now 0.7. Okay? But that's on the side of it. The thing is, what should we charge this guy then? He's got 1 unit. What should we charge him? 0.5. 0.5. Yeah, we should charge him 0.5. But he's got utility of 0.
That's his problem.
That's his problem, perhaps. But it means that the solution is not individually rational. So if he knew that in advance, that that's what's going to happen, he would report value 0 and not get any units, because he's better off in that way. Okay.
Why
So-
not 0.9? And so he can get both slots.
Yeah, okay, so what would his payment be then?
What? 0.9.
You'd have to pay, actually, you'd probably have to pay 1.4 actually.
Okay, for both slots. Not
Yeah.
for, okay.
Yeah. But even if you just pay 0.9, he already pays more than his value. So his value is not per unit. Okay? So his value is, I get 0.7 if I get both, and 0 otherwise. So even if he would pay 0.9, he would be making loss. Okay? So if you report 0.9, in fact, you're right, he would get both units, but he would be paying too much again.
Yeah, but so normally you have him pay so much as to cover for the loss of social welfare, wouldn't you? Like, so if you gave him nothing, player 3 would buy it for 0.5, player 1 would buy it for 0.9, both would be happy and the other guy would go home. So now you give one to player 2,
Yeah.
which actually does nothing for him,
Oh, yeah,
because of player 3 as well.
but if this player wasn't in the market, B1, right? You would want to give it to him.
Yeah.
But you don't know that when you're here. That's the problem. So if we're looking at, okay, so we're looking at greedy, right? We can't, greedy doesn't work in this case anyway. Maybe there's other mechanism that would work. But greedy, which gives it, say, to the person here, doesn't really work. Even if we find other mechanisms, it's a bit tricky.
First come, first served.
First come, first served, yes. Yeah, that works, yeah. That works. Okay, so where am I at? So, in a sense, greedy doesn't really work in this case anymore. But we can adjust greedy. Okay. So this is about unknown. So therefore, greedy allocates 1 unit to this guy and 1 unit to that guy. His payment, because suppose he says, I wanted 2 units, right? But I only get 1 unit, so you can't charge me for this. Okay? So the payment has to be 0. Right? Because you only get 1. Huh?
Can send it to player 3.
No, there's no reason. So B2 gets the item, that's what we're looking at, and then B1 gets the item, but B2 pays 0, because his utility is 0. To be able to get it, it's compatible, you can't charge any more than 0. Okay? Now suppose that he only, in fact, he only wants 1 item, but he says he wants 2. Okay? Because he says he wants 2 items, he gets this item for free. That's why we need to know the interesting set. So what can we do if we know the interesting set? Okay. If we know that's the interesting set, we can easily charge him 0, and that's fine. Okay? Because we really know that he wants 2 items. So if that's common knowledge, that the mechanism designer knows that, we can charge him 0 and we don't break the incentives. Because it's value was 0 for that, so we charge him 0. And we can solve it that way. But if we don't know, we have to find a slightly different mechanism. So we can do 2 things. Okay, so that will be the last one. So what can we do? How can we solve this? So greedy in itself doesn't work. We have to adjust it somehow. How can we adjust it? Any idea? Suppose we could have the power to allocate the item, but then once we come to the end, we can take away the item again from the agent. Okay?
So essentially we would be doing the auction in reverse.
Almost, a little bit. Sometimes, yeah. So we look at the agents and all the parts of the agent. We look what would, given his report, right? If he would get this item, he would have to pay 0.5. Let's say, right? This is the critical value. He prefers not to have that item. So we take away that item from his, and he doesn't pay it. So this is called a cancellation. So after the fact, we cancel. So the problem is, so that's fine, everyone's happy, right? So, well, it's not completely happy, because we've taken away an item, and we've not allocated to anyone, right? So what happens here, this guy gets the item, this guy gets another item, and at the end we take away this item. What can we do with this item? Well, we can't reintroduce it into the market, because that breaks incentives as well, actually. Just trust me. So actually we have to throw away that item. We can't allocate it to anyone else, because otherwise people could manipulate it in some way. So this is wasted. That item is wasted. So it's fine, it works, it's truthful, but first of all it's wasted. Second, suppose this is this battery charging environment. So we're looking at electric vehicles, we're charging the battery, so here we've got the battery half charged. The second, we decide not to give him the underwriter. At this point, we have to take away this allocation. We have to discharge this battery.
Or take it.
Or take it. Or explode. So, it's possible, but it's not always desirable to take away the item. So, especially with perishable goods, it's not always possible. But even with computational resources, you can find something. So you can maybe compute an allocate solution, and then you don't give the solution to the agent. Just throw the solution away. But anyway, there's ways you can do it, but you have to find in a specific domain what it means for something to throw away or to take back an item. So, so we could do that, but there's a better way.